In this video, we're going to look at a new technique called the integrating factor. Okay, and it's a technique to solve first order differential equations. And we've already got one technique for solving first order differential equations, which is separation of variables. So say, for example, if we had dy by dx equals 3xy, that's a first order differential equation. And we could solve this without knowing this integrating factor technique, because there are two terms and we can use multiplication and division to separate the variables. We can divide throughout by y, and that would leave me with 1 over y. dy, multiplying up by the dx, leave the 3x with the dx, and then we've isolated the y terms on the left with the dy, the x terms on the right with the dx, and then we can integrate. Okay, so that's like a standard A-level maths technique, which is separating variables, and then we just integrate both sides. But in further maths, we're going to look at different types of differential equations. And if it's in this form, where it's dy by dx, some sort of function of x multiplied by y, so these two terms are linked together, and then equal to another function of x, we've got an equation with three terms in. And you can try if you want, like if you want to pause the video, maybe try and separate the variables for this to get the y with the dy, the x terms with the dx, but just trust me, you are not going to be able to separate variables on this, which is why we need this new technique. I think the best way to approach this is just to do a couple of examples. There is a proof on why this works, which I normally go through, but I'm not going to do it on the video. There's a proof in the booklet, so you can have a look at the booklet if you're interested in the proof. You won't need to know how to do the proof in the exam. It's more just about actually, this is a standard exam style question. Separate variables, use the integrating factor, solve this differential equation. Okay, so let's just try example 1. First thing, very important thing to notice, right? This form that we're looking to use the integrating factor on, the coefficient of dy by dx is equal to 1. So this first one, we need to rearrange before we can even use the integrating factor. So if we divide throughout by x, that would give me dy by dx plus 2 over x, y. You will see why it's nice to, instead of writing it all divided by x, think about what's being multiplied by y, and then equal to 4x on the right hand side. So the first step is to make sure that the coefficient of dy by dx is equal to 1. Then we find our integrating factor by doing this calculation. Okay, so this f of x is basically the function that's being multiplied by the y term. So when we've got it in this form, look at what's being multiplied by the y term, and that's where you're going to get your integrating factor from. So it would be e to the integral of this function, which is 2 over x, with respect to x. So we're integrating a fraction. I know 1 over x is ln. Take the multiple of 2 outside. And then when we integrate 1 over x, we've got the derivative on top, so that becomes ln x. Now we know the e and the ln cancel, but before we do that, we need to use a log law. Don't forget ln is just a natural log, isn't it? Number in front becomes a power, so that would be e ln of x squared, and then because these are inverse functions, they cancel each other. So our integrating factor is x squared. Okay, so that's the first step. Find your integrating factor. Once you found your integrating factor, the second step is to go back to this equation. A common mistake that people make is they go back to the original one. Don't do that. This is our question that we're working with now. We just divided throughout by x, and this is our question that we're working with. So once we found our integrating factor, the second step is to multiply the whole equation by the integrating factor. So that would be x squared dy by dx plus, multiply that by x squared, that becomes 2x y. And a lot of people forget this, I'm not sure why, but don't forget to multiply the whole equation, so that would be 4x cubed. Okay, so step 2, multiply your differential equation by the integrating factor. Now, as if by magic, the left hand side will always be the derivative of the integrating factor, which is x squared times y. In the proof we can see why this works, but just trust me that this will always work, and it's good to check. So what's going on there, right? So step 3 is to write it as the derivative of the integrating factor multiplied by y. And this step takes students a little bit of time to get used to, so let's just think about this for a second, right? Look at our original differential equation, and then look at what it looks like when we multiply by our integrating factor. We've got x squared dy by dx plus 2xy. Now if I asked you, remember this notation just means differentiate with respect to x. If I asked you to differentiate x squared y, we'd have to use the product rule. And we would get x squared times by dy by dx, because that would be the derivative of this. Remember, it's u times by dv plus v times by du. So if we use the product rule on this, that is actually what our answer would become. Just rub it out. So you're just gonna have to trust that this will always work, but just bear in mind that just check, like it's a nice way of checking, like did I get the correct integrating factor? So I found my integrating factor, I've multiplied by it. You will, once you've done a few of these, you'll sort of automatically jump to, oh, it's just the integrating factor times by y. But just check, like if I differentiate this, that is the same as those two separate terms. Okay, so just trust me, this will always work. And now we'll see like why this is important, because once we've got it written in this form instead of that form, we can actually begin to solve this differential equation now. Okay, so what we've got is d by dx of x squared y is equal to 4x cubed. And remember, we're trying to find the general solution, so we want to solve this equation. That instruction is to differentiate. So what we now do is we integrate both sides with respect to x. Now if I integrate the left hand side, I'm integrating and I'm differentiating, and they just cancel out. So on the left hand side you're left with just x squared y. And obviously if we've integrated the left hand side, we integrate the right hand side with respect to x. So all we've really got to do now, just to finish this, is actually just integrate this simple integral on the right hand side. Add 1 to the power divided by the new power, so that'll become x to the 4 plus a constant. Do not forget a constant, it's important that we remember that. And then divide throughout by x squared, so y would become x squared. The constant needs to be divided by the function as well, so that would be c x to the minus 2. Okay, there's a lot going on there, but we'll do a few more of these, and it's basically a standard method that after you've done a couple of them, hopefully you'll feel okay with this. Alright. Okay, so example 2, we've got something straight away in the correct form, so it's dy by dx, a function of x times by y, and then a function of x on the right hand side. So we could just look at this and see, okay, so maybe if you write it as minus tan x times by y, that's going to be our f of x in this question. So let's calculate our integrating factor. So it'll be e to the integral of minus tan x. Now I'm going to write it as minus sin x over cos x, because I'm trying to integrate this and it's a fraction. And if you think about it, if I've got a fraction, if I differentiate cos, I'd get minus sin, so the derivative is on top. So this is going to become an ln, just using f dash of x over f of x. Okay, so the derivative is on top straight away. So that would give me e ln cos x. And then they cancel out, so cos x is what my integrating factor is. Once you found your integrating factor, multiply your differential equation, as long as it's in the correct form, multiply this form by your integrating factor. So we'd get cos x dy by dx minus, now tan x is sine over cos, so if I multiply by cos, that would be minus sin x times by y. and I'm multiplying it by cos as well, so that'd be 3 sine squared cos. Now you don't need to check this, but just think about it. Like you know that you're always going to get the derivative. Like the way the integrating factor works, this left hand side will always be the derivative of the integrating factor, which is cos x multiplied by y. But just check, like, just is this thing here the same as this thing? Because that's all we're really doing. We're just rewriting it in a different way. And once we've rewritten it in this way, we can integrate it. Okay? So if I differentiate this, use the product rule, leave that one alone. So u times by dv, yeah, that'd be dy. Then you differentiate this one, yeah, you get minus sine, leave that one. Yeah, it's right. So that there is equivalent to that, which means you know you've got your integrating factor correct. Okay, nearly there. Last step, once you've written it in this form, is we just need to integrate both sides. Okay, so I'm going to write this as y cos x, to cancel the derivative, and then actually we're just integrating the right hand side, aren't we? So if I integrate that side, it cancels, integrate this side with respect to x. And this is, with a bit of practice, the only place people get stuck is really this point now. Because obviously now we've just got an integral, and we've got to be good at our integration to be able to answer this question, because there's loads of different scenarios that can happen on the right hand side. Okay, maybe pause the video just for a second and think about how you could integrate this. Okay, so what we're thinking, we've got two functions times together, maybe parts. Parts would be a bit of a mess with two trig terms. The one thing that I've spotted for this, if I take the 3 outside, I've got a function inside another function, so it's sine squared. And that is perfect for a substitution. If I let u equal sine x. Remember, with integration, if you've got a function inside another function and it's not linear, you can pretty much guarantee it'll be substitution. The even better thing about this is when you spot that there's something inside this, whatever you choose for your substitution, remember your first step is to differentiate. And when you differentiate, you get cos. And you've got the derivative here, so I know that stuff's going to cancel and this substitution is going to work really well. Okay, so once we've spotted the substitution, let's see what happens. That's just u squared cos x. dx is du divided by cos x. Tidy up. Cos cancels, and we're left with just integrating u squared with respect to u cubed over 3 plus a constant. Let's tidy this up, and we've got y cos x. The 3's are cancel. What was u? Sine, so that would be sine cubed plus a constant, and then I suppose we could divide by cos. If we wanted it in the form y equals. Dividing everything by cos, you can write it as 1 over cos, or you could also multiply by 1 over cos, which is just sec. It might say in the exam, like, write it in a certain form. It might also ask you to find the constant. I think we'll probably look at that on the next exercise, though. For now, we're just going to practice this integrating factor technique. Okay, I'll do one more on this video. As I say, once you've done a couple of them, it's like a standard method. It just takes a little bit of practice. Okay, if you're not feeling too confident, maybe pause and go back and watch this example again, and then, or the first example, but we'll try one more in a second, guys. Okay, example 3. We're actually given a coordinate as well, so we will be able to find a particular solution. We'll find our constant once we've integrated. So we've got x dy by dx minus y is equal to 2x cubed. First, most important step, don't forget this. Like, this could potentially be like a 9-mark question, and I've had students in the past who've not divided by x, like, and just try to do the integrating factor, and you just basically get no marks, or pretty much no marks. You might get 1 or 2 if the examiner's feeling generous. Get it in the correct form, and then you'd get 2x squared. Okay, so we've got it in the form. There's where my integrating factor is going to come from. So So it's e to the integral of minus 1 over x. I'm going to take the minus outside because I'm thinking about integrating this, and I know if I integrate 1 over x, I'd get ln x. So that would be e minus ln x. Just be careful, we want the e and the ln to cancel. Bring this up to the power. So that would be x to the power minus 1. The inverse functions cancel, and you're left with x to minus 1. You might want to write it as 1 over x, it's up to you. Whatever you do now, once you find your integrating factor, make sure we go back to this. I need some new pens. Make sure you go back to this, because that's what we're going to be multiplying by. That's the differential equation that we're working with. Okay, so what's it look like? 1 over x divided by the x minus 1 over x squared y equals 2x. Just pause and check. That should also always be the derivative of the integrating factor, which is 1 over x times by y. If you want to check, if you differentiate this, use the product rule, it will go back to this. Okay. On the right hand side, we've got 2x. So now we've got it in a form that we can integrate. And we just got a relatively simple integral on the right hand side. Add 1 to the power, divide by the new power, don't forget your constants. We can find the constants. I suppose we could find it at this point, we could rearrange and we could find it. I normally prefer that once I've integrated, I normally find my constant straight away and then I rearrange afterwards. Just make sure you get that in that way, you definitely get your method mark for your constant then. So if x equals 1, y equals 4, we've got 1 over 1 times 4 equals 1 squared plus c. 3 would equal c. So whenever you found your constant, sub it straight back in to the line that you were working with and then just rearrange. I'm guessing in this case it would say in the form y equals multiply by x, so it'd be x cubed plus 3x, and that's our particular solution to our differential equation. Okay, let's see, I'm going to leave it there for this video, but oh actually, that's perfect. So that's the end of those examples. You're ready to try exercise 1, guys. Couple of challenging integration techniques on there, but the work solutions are provided. So let me know if you need any help, and have a go at exercise 1. Okay, thank you.